Hello everyone, welcome to IIT and GATE classes. This is lecture 12 on operating system, and in this lecture we are going to start hardware based solution of critical section problem. Hardware based solutions of CS problem. If you try to remember, in my previous lecture I have completed software based solutions. So in software based solutions neither hardware nor operating system was helping. Okay, but in hardware based solution, as the name suggests, hardware is going to help us in implementation of critical section. Okay, so here hardware will help. Okay, so now you will argue, sir, how hardware can help? Okay, so let me tell you that thing. Hardware will help in implementing CS. In implementing CS. Okay, so how it will help? Let me give you an idea. So we will make a function. We can make several functions, and I am giving you idea of one such function, that is test and set. Okay, so test and set is a function in which we will give an argument called lock. You can give any name. See, this is a function, so we can give any argument. We are giving a lock variable. Okay, and lock is a boolean variable. Okay, so since lock is a boolean variable, so it can take value either true or false. Okay, so when lock is false, then what will happen? When first time, see, there may be multiple processes who are calling this test and set function. So when first time it is called, first time test and set called, test and set called, it will return false. It will return false. But for subsequent calls, it will return true. Are you getting it? So when lock is false, then for first time, whenever first time test and set is called, it may be called by any process. It hardly matters to me. The only thing is whenever it is called for the first time, then it will return false. But for the subsequent calls, it will return true. Okay. And when lock is true, then it's very obvious. It will keep on returning true or only. Okay. Keep on returning true. Keep on returning true. So the basic thing is for the first time when lock is false, then for the first time test and set will return false, but for the subsequent calls it will return true. And when lock is true, then it will keep on returning true only. Are you getting it? And I'm not going into detail how this test and set function is made and so on, because it is a basic course. So we will not unnecessarily dig deep into the topics. Okay. So basic thing is test and set lock. You can say it is hardware implemented function. Hardware implemented function. Hardware implemented function means it is atomic. Atomic means we can't imagine interrupt while execution of this function. That is, we can't imagine interrupt while execution of test and set. While execution of test and set function. Okay, so when test and set function is executing, we cannot imagine interrupt. That is very important point, because you will get confused after a few slides. So please try to focus here. Okay, yes, take snapshot. I will jump to the next slide, and now I am going to show you the solution to critical section problem. Now test and set we have understood properly, so let me tell you the solution. I'm jumping to next slide. Please take snapshot. Okay, so now straight away I am going to give you n processes critical section problem solution. Okay, n processes CS solution. Straight away I am giving you that. If you try to remember, in software based solutions we have given only 2 processes solution. Okay, no doubt in software based solution we have n processes solution also. Okay, but we are not going into detail of that. And we are now starting hardware based solutions, and in hardware based solutions straight away I am giving you n processes CS solution. So how does it look like? Let me tell you that thing. So we have a lock is a shared variable. as I have told you, lock is a shared variable and it is initialized to false. Okay, and they are saying do while test and set lock semicolon cs lock is equal to false while 1. Okay, so this is the code of any process, so you can take it as pi process. So when for pi process we have this code, so I think you have got it. Each and every process will be having the same code only. Okay, you can copy it and paste multiple times here and there, that's all, and so on. So for each and every process this is the code. Okay, so now we have to check whether this is good solution or not for this critical section problem. Okay, so we have to check three conditions. What are the three conditions? Mutual exclusion, progress, and bounded waiting. So please tell me what about mutual exclusion. Mutual exclusion means only one process should enter into its critical section. Okay, we cannot say two or more processes must not enter. Okay, so initially lock is false. So imagine all the processes come like PI, PJ, and so on. All processes come and they try to execute this test and set function. So what I have told you, see, only it will return first time it will return false. Otherwise, it will return true. Lock is false now. That's why only first time. See, no doubt many processes are coming parallelly, but we will imagine that we have only one CPU. Since only one CPU is there, so obviously, uh, exactly one of the process should have come first. Are you getting it? For example, you can imagine time is 10 a.m. So at 10 a.m., you will imagine only one process is there. Now at 10:01, after 1 second, one more process comes. After one more second, one more process comes, and so on. So no doubt there are multiple processes, but only one of the process will exactly same instant. I am using the word exactly same instant. Exactly one of the process should have come. Okay, so only so for that process, test and set function will return false. But for other subsequent processes, see first process, it will return false, but for other processes, it will return true. Okay, so for 10 a.m. process, that means first process, it has returned false. So that means what? This loop is broken. Test and set lock, this function has returned false. So while false means what? Loop is broken and it enters the CS. But for subsequent processes, it will return true. So test and set lock, they each and every process will keep on doing this, and they will just, you can say, revolving here only. Okay, they cannot enter the CS. Okay, yes, and test and set will directly indirectly it will make lock to be true. Okay, so for first time it has returned false and it will make lock to be true, and for subsequent calls it will return true. Are you getting it? Let me write that point also. Please do not get confused. First time test and set called, it will return false and make lock to be true. And make lock true. Okay, it will make lock to be true. Are you getting it? Okay, so for subsequent calls, for subsequent calls, it will return true only. Okay, so now please come here. So the very first process which arrives at 10 a.m. So test and set lock it has done, and lock has returned false. Because lock has returned false, so it will enter the CS, and now lock has become true. Okay, so now when it is in CS, all the other processes whichever come on 10:1, 10:2, 10:3, and so on, whatever processes are coming, they will keep on rotating here only. They cannot enter the CS. Okay, why? Because lock is true. So lock is true, they will say test and set lock, so it will keep on returning true, true, true. So they will keep on rotating in this loop. Okay, so now when the process which comes at 10 a.m. it comes out of CS, it will make lock to be false. The moment it make lock to be false, one of the process which were waiting in this area, one of the process will see lock to be false and it will try to enter CS. Are you getting it? So directly and indirectly I can say mutual exclusion is satisfied. Okay, and progress, how progress is satisfied? Yeah, this is satisfied obviously. Why? Because only those processes will enter which are waiting here. Okay, if process is not waiting here, like for example, if process is here, it is in remainder section, this is the remainder section. So it will not enter. It's obvious, na? The process which are here, they are stuck in this loop. All the for the and one of the process will enter into the CS. Okay, one of the process from this one of the process will enter into the CS, and which process will be that we really don't know. But the thing is that only those processes which are here, okay, which are present here, or they are executing this loop, they are keep on executing this loop, only those processes, one of those processes will enter into the CS. So directly what I will say, the process who wants to enter into the CS, only that process will enter. Okay, the process which do not want to enter in CS, like it is in remainder section, it will not enter CS, obviously. Okay, or rather it will not participate in decision making, who will enter the critical section next, and so on. So only those processes are participating who wants to enter into their CS. Okay, so progress for willingness part is over. Okay, so now we have to consider time. Okay, willingness means process will willingly enter into the CS. Na? The process who is not willing to enter CS, he is not participating in any decision making and all. Okay, what about time boundation? Yeah, time boundation is also there. See, there is no deadlock kind of thing. Exactly, one of the process will see log to be false and it will enter CS. Rest every process will keep on saying it as true, true, true. Okay, so one process will definitely enter into the system. So there is no deadlock kind of thing. So time boundation is also satisfied. So clearly progress is satisfied. Okay, what about my bounded waiting? Bounded waiting, see, bounded waiting, for bounded waiting, what I have told you, when one process is in CS and other process is waiting outside CS, that means it is here in spin lock. It is, you can say, executing this loop again and again. Okay, and when the other process comes out of CS, then it should not enter again. But here it can enter. Rather, there is no rule and regulation. For example, see, we have P1 process, P2 process, P3, P4, P5. Okay. So now assume P1 is in CS. P1 comes out, P2 goes. P2 goes out, P3 goes. P3 goes out, P4 goes. And then again P1 goes, then P2 goes, then P3. Okay, then P2, then P1, then P3, then P2. There is no hard and fast rule. So it may happen that P5 is never getting its turn. That is also possible. So clearly I should say that algorithm is not deterministic. Algorithm is not deterministic. That means by seeing this code, I cannot guarantee who will enter the critical section next. So directly and indirectly, I will say bounded waiting is not satisfied. Why? For example, when P5 has requested to enter CS, the number of processes entering into the critical section is not bounded. They can go as many times as they want. And it may so happen that P5 never get its turn. So bounded waiting is not satisfied. So I hope I have made the point clear to everybody. Yes. So the only thing is you should know what test and set is doing. Okay. So what test and set is doing? So first time test and set is called, it will return false and make log to be true. Okay. So obviously for subsequent calls, it will keep on returning true. For the very first process, test and set, simply I can say for very first process, test and set will return false. For rest of the processes, it will keep on returning true. Okay, and when we have made this log to be false, then obviously we are at the initial situation only. So for one of the process, it will return false. For rest of the process, it will return true. Okay, so that's why I have said. So for example, when P1 is in CS, P2, P3, P4, P5, all are waiting outside CS. That means they are here in this loop only. And when P1 comes out of CS, it will make log to be false. The moment it make log to be false, one of the process P2, P3, P4, P5, one of them will see log to be false and they will enter the CS. I think you have got the point. So please take snapshot. I will jump to the next slide now. Okay. Yes. So now this was not good solution. Why? Because bounded waiting was not satisfied. So now let me show you the correct solution. Okay. So how correct solution is made? Please try to focus here. So for PI process, I am writing the code. Okay. Yes. So for PI process, I am writing the code. What code is saying? See, we have a waiting array where waiting is an array of 0 to n minus 1 of Boolean type, and it is initialized to false. Okay. So that means directly and indirectly, none of the process is waiting to enter in CS. Okay. That's why all array 0, array 1, array is the data type now. So I will say waiting 0, waiting 1, waiting 2, waiting 3, and so on. So waiting of each and every process is initially false. That means none of the process wants to enter in CS. Okay. and I will say waiting. We have a Boolean variable called lock. Okay, so we have a lock Boolean variable and it is initialized to false. Please do not focus on syntax, what I am writing and all. I am just giving you idea. This is an algorithm. You can consider this as an algorithm. It is not a program. Okay, so do not say, sir, there is syntax error and all. Okay, yes. So initialize to false. Okay, Boolean variable is lock and it is also initialized to false. Okay, so now we are going to write code. Okay, so I should write it here. Okay, so these are the shared variables. So now I will write the code for pi from here. Okay, so what is the code? What it is saying? Where j is equal to 0 to n minus 1. That means a variable j we have defined and it can take values, any value from 0 to n minus 1. We have a key. It is also a local variable of pi. Are you getting it? Pi process code I'm writing, and for pi process, these are the shared variables. That means global variable you can consider, and these are the local variable of process pi. So j is equal to 0 to n minus 1. That means what? J can take any value from 0 to n minus 1. Key is also a local variable and its type is Boolean. Okay. And waiting I is equal to true. That means what? Pi waiting I true means what? It wants to enter in CS. That means it is waiting to enter into the CS. Okay. And then we will make key to be true. Are you getting it? We will make key to be true. And then we will say while waiting I, while waiting I and key, do key is equal to test and set lock. Okay. And then we will say waiting I to be false and then CS. Don't worry, I will explain you what I'm writing. Then we will say j is equal to I plus 1 mod n. Let me write it properly. J is equal to I plus 1 mod n. Okay, and then we will say while j is not equal to I, this code is no doubt huge, but you will be able to understand it. Please have some patience. While j is not equal to I and not waiting j, do j is equal to j plus 1 mod n. Okay, j is equal to j plus 1 mod n. If j double is equal to I, then log is equal to false, else waiting j is equal to false. Okay, code is no doubt huge, but you will be able to understand it. Please bear with me for just 2-3 minutes. You will get each and everything clearly. So for pi, what we have written the code for pi, we are saying where j is equal to 0 to n minus 1. These are the, you can say, shared variables which are visible to each and every process. And for pi, we are defined a local variable where j is equal to 0 to n minus 1. That means it can take any value from 0 to n minus 1. Key is a Boolean variable, waiting I true. That means what pi is wants to enter in CS, it will make key to be true and it will say while waiting I and key. It is so obvious, na? Key you have just made it true and waiting I you have just made it true. So obviously it will be true. True and true is true. It will say do key is equal to test and set lock. So now it entirely depends on lock. Okay, what you are going to get, it entirely depends on lock. So if you are the first process, so you will say lock to be false. I have just told you what test and set is doing. If you do not remember, please see this. First time test and set is called, it will return false and make lock to be true. Okay. So test and set will return false. So that for the first process, so key will become false. Okay, you know that you have made key to be true, but now here you have made key to be false. So now this statement is in the loop now. While waiting I and key do key is equal to test and set log. So this thing is, say this is the body of this while loop. Okay, so we will say key is equal to test and set log, and log is false initially. So test and set function will return false. So key will become false. When key will become false, then you will check waiting I. Waiting I was obviously true, and key is false. So that means what, your loop is broken. Loop is broken, and you will say waiting I to be false. Why waiting I to be false? Because now you are going to enter in CS. Now you are no longer waiting to enter CS. So that's why we have written waiting I to be false, and the process enters the CS. So I am assuming the very first process it has entered the CS. Now, what about rest other processes? They will come, say for example, PJ come, PK come, whatever process we are imagining, they will come. They will initialize this. They will define a variable j. 0 to n minus 1 key is boolean. Waiting I to be true. Key is equal to true while waiting I and key. Do key is equal to test and set log. So first process has entered the CS, and your log has become true, and when other process will access, they will find log to be true. So test and set will return true. So they will make key to be true. So while waiting I is true, uh, whatever may be the process. So for PJ, you will write waiting J. Okay, whatever you want, you can do. So I am just using the word other processes. So other process will see its waiting will be true. Okay, and key is also true. You have just made it. And when you enter the loop, body of the loop, what you will see, key is equal to test and set log. Log has become true now. The first process has entered the CS now, so it has made log to be true. Its test and set function has made log to be true. I have told you, I am repeating again and again. Test and set function, when log is false for the first time, it will return false for, and it will make log to be true, and for subsequent calls it will return true, true, true. For first call it will return false, for rest of the calls it will return true. So obviously for other processes, test and set will return true. So key will be true only. So true and true is true. So so processes will keep on rotating in this part only. No one will enter CS. Okay, so first process is in CS, and rest other cannot enter into the CS. So I hope I have made the point clear to everybody. Yes, so obviously mutual exclusion is satisfied. Okay, because only one process is entering into the CS. Okay, now, so now the process which is in CS, now see carefully, the process which is in CS, when it comes out of CS, what it is doing, this is the very beautiful part. It will say J is equal to I plus 1 mod n. For example, say we can have P0, P1, P2, P3, P4, P5. Okay, so let us imagine we have 6 processes, P0, P1, P2, P3, P4, P5. Okay, so I am assuming that, say, P3 is in CS. Okay, so first, at the very first time, obviously all wants to enter, but the very first time P3 comes. So because P3 comes, so P3 will see log to be false, and its test and set will return false. So it will enter into the CS. But rest of the processes, when they will come, they will keep on rotating in this loop itself. So now when P3 is coming out, now see this very, very beautiful point. J is equal to I plus 1 mod n. So so P3 was there, na? I is 3. Okay, P3 means what? I is equal to 3, na? Okay, so yes, so when P3 is coming out, so it will make J is equal to I plus 1 mod n. That means it will make J to be 4. Are you getting it? So initially we are having I is equal to 3. Now J you have made 4. Why you have made J 4? J is equal to I plus 1 mod n. That's why. And why we are doing mod n? Because we will keep on checking each and every process. So when we will come to P5, then we will jump to P6, but P6 process is not there. We have to jump to P0. So that's why we have done mod n kind of thing. So there are 6 processes. So we will say when on P5, so I will say 5 plus 1, that is 6, 6 mod 6, that will be 0. So J will become 0. I think you already know all these things. These are very basic things. Okay. So modern just to implement circular fashion. Okay, now J is equal to I plus 1 mod n is over. So that means we have got J is equal to 4. So now we will say while J is not equal to I, forget about J is not equal to I. You just see this, not waiting J. Okay, so if P4 is not waiting to enter in CS, so obviously it's not waiting will be true, na? Are you getting it? See, this is very simple scenario. Please do not get confused. I am going to check for P4. Okay, so I will say not waiting P4 is true. Not waiting P4 is true means what? Its waiting is false. Its waiting is false means what? It does not want to enter CS. Are you getting it? See, if P4 wants to enter CS, it will make its waiting to be true. Now, if P4 does not want to enter in CS, initially we have done everything to be false. Now, every waiting element is false. So P4 will be false. Okay, P4 waiting will be false. So now P4 waiting is false. So I will say not waiting for P4 will be true. So while true, that means what? We will execute this loop. Okay, and obviously J is not equal to I here. J is 4 and I is 3. So true and true is true. So we will come into inside the loop. So do I will say J is equal to J plus 1 mod n. So I will keep on doing this thing. J is equal to J plus 1 mod n. Okay. Yes. So see, actually body of while loop is still here only. Okay. This is outside while loop. Outside while loop. Do not get confused here. Okay. Yes. So J is equal to J plus 1 mod n. So now it will become 5. So you will say J is not equal to I. Okay. 3 is not equal to 5. Yes. Not waiting J. I am assuming P5 does not want to enter CS. So you will say J is equal to J plus 1 mod n. So 5 plus 1 mod 6. It will be 0. Okay. Please try to focus here. 5 plus 1 mod 6. It will be 0. So now you will check P naught. Are you getting it? So one by one, please see, focus here. P3, what P3 is doing? When P3 is coming out of CS, it is checking one by one which process wants to enter into the CS next. It is checking one by one. Okay, so it will check P4, then P5, then P0. Okay, now let us assume P1 wants to enter CS. So assume P0 does not want to enter CS. Are you getting it now? P3 is checking P4. I'm assuming P4 does not want to enter CS. So you have made J is equal to J plus 1 mod n. So it will become P5. See, initially J is equal to J plus 1 mod n. What was its use? It has just made plus 1. So initially P3 was there. So P3 is going to check P4 first. Now that's why you have done J is equal to I plus 1 mod n. So it will be 4. Okay, now J is equal to I plus 1 mod n. We have done it. So now we are checking this loop. So we are keep on checking processes one by one who wants to enter the critical section next. P3 is checking one by one. I hope you have got it. Okay. So now P4 does not want to enter. So you will say J is equal to J plus 1 mod n. P5 does not want to enter. So you will say not waiting P5. Not waiting for the P5. So you will say yes, it is true. So J is equal to J plus 1 mod n. So it will become P0 and then it will become P1. Finally, we are at P1. So now let us assume P1 wants to enter CS. So it will say not waiting J, not waiting 1. So no, it is false because P1 wants to enter CS. So loop will be broken. Loop will be broken and we will first check this thing. If J is equal to I, then lock is equal to false. Forget about this line first. Else, J is not equal to I na here. So you will say waiting J is equal to false. Yes. So you will make P1 waiting for P1 to be false. So when it will become false, control will come to P1 and P1 will say P1 was waiting here na. So its loop will be broken because waiting is false. Lock is true only. Waiting is false. So it will enter the CS. I hope you have got the point. Okay. So that's how P3 will keep on checking each and every process, and process who wants to enter CS, for that P3 will allow that process to enter into the CS. Are you getting it? P4 does not want to enter, P5 does not want to enter, P0 does not want to enter, P1 wants to enter CS. Now if P1 wants to enter CS, now what you will say, you will make its waiting to be false and it will enter into the CS. So directly what I'm saying, P3 is deciding, the process which is coming out of CS is deciding which process will enter the critical section next. And it is very fair game. Why fair? In the sense because the process who wants to enter CS, only that process will enter. So directly and indirectly progress is satisfied and there is no deadlock kind of thing. You can check it out yourself. Each and P3 is checking each and every process one by one. Now assume if no one wants to enter CS, if no one wants to enter CS, now say P3, say P3 is coming out of CS, so it will make J is equal to I plus 1 mod n. So it will now check P4. So let us suppose P4 does not want to enter CS, so J is equal to J plus 1 mod n. So it will become P5. So now assume P5 does not want to enter, then P0, then P1, then P2. Now you will come to P3 again. Okay, now you will come to P3 again. And now you will say J is equal to I. Are you getting it? You will get J is equal to I. So immediately loop will be broken. Okay, so now assuming none of them wants to enter CS. So that means for every process waiting is false. For every process waiting is false and J has become I. So what I will say, I will come out of this loop. So now there are two reasons of coming out of the loop. Either j is not equal to I or not waiting j. So when not waiting j was there, so we have made j to be false, waiting j to be false. But if j is not equal to I was the reason, so that's why I am checking outside now. So see, we are coming out of while loop, but we do not know what exactly is the reason. So we have to check it out. So we are checking that j is not equal to I was the reason or not waiting j was the reason. So for that we have applied if condition here. So if I will say if j is equal to I, that means what? Both are equal. So when both are equal, then obviously loop we will come out of the loop now. So when both are equal, then I will say log to be false. Log to be false means you come back to the initial situation. You come back to the initial situation. That means this. Okay, so none of them is waiting and lock is also false. So whenever any process wants to enter CS, it will definitely enter because lock was false. No doubt it will make waiting to be true, key to be true, but lock is false now. That's why it will enter CS and so on. So I think you have got it. So mutual exclusion is satisfied. Progress is also satisfied. There is no deadlock kind of condition. Each and every process is checking other processes and so on. Okay, and willingly. So the process who wants to enter CS, only that will enter. Na? So P3 will check P4, P5, P0, and if P1 wants to enter, then it will enter and so on. So willingness, everything is perfectly fit and fine. Bounded waiting, I think you have automatically got it. Bounded waiting is satisfied here. Why bounded waiting is satisfied? Because see, when P3 is in CS and P1 has requested to enter CS, let us suppose P1 and P0 both have requested to enter CS. P3 is in CS, P0 and P1 both have requested to enter CS. So now what will happen? P3 will check P4. P4 does not want to enter. It will check P5. P5 does not want to enter CS. Now it will check P0. P0 will enter CS. Now when P0 will enter CS, this is very, very important point. When P0 will enter CS and when P0 is coming out of CS, it will make P0 I is 0 na. So it will make 0 plus 1, that is 1. 1 mod 6 will be 1. So it will check P1. Are you getting it? So P0 will check first, P1 only, and P1 will enter CS the next. So are you getting it? When P3 is in CS and P0 and P1 both are waiting to enter in CS, then it is guaranteed that first P0 will get its done and then P1 will get its done. So directly and indirectly, this algorithm is perfect case of determinism. So it is deterministic algorithm. Now, since it is deterministic algorithm, so obviously we can say that bounded waiting is satisfied. Okay, because there is a complete system who will going to enter next and so on. There is complete system. That's why. Okay, now you can take snapshot. Okay, and I will jump to the next slide. And I hope everything is crystal clear to everybody. Okay, yes, now everything is on one slide. You can take snapshot. Okay, now, so this is all about your end processes critical section problem. That is a correct solution with the help of a hardware-based solution. Let me jump to the next slide now. Okay. So now we are going to start. So hardware-based solutions are over. Now we are going to start OS-based solutions. Are you getting it? No, we have done 3 types of solutions. Okay, solutions were of 3 types. One was software-based solutions. We have completed in the last lecture. Next is hardware-based solution, and next is OS-based solution. So software-based solution in the previous lecture we have completed. Hardware-based solutions we have just completed now. That means hardware was helping us. How hardware was helping us? We have designed a special function called test and set, and we will imagine that it is a part of hardware. So directly and indirectly, we will not imagine any kind of interrupt. Okay. Yes. So next is OS based solution. So now we are going to start that. So OS based solution means OS is going to help in implementing CS. Okay. So now let me see. Let me say how OS is going to help in implementing CS. So in that, so in this topic, OS based solution, we are going to study the most weighted topic. I think you all might be waiting for the semaphores. So semaphores will be studied here. Okay, yes. So first of all, before starting semaphore, we should have an idea that what exactly is semaphore. Okay, so if you know exactly what are the semaphores, then obviously you will be able to understand each and every concept. But if you are not able to understand what exactly are semaphores, then it's not guaranteed that you will be able to grab all the concepts which I'm going to tell you now. Okay. So first of all, semaphore, you should know it is nothing but a shared variable. Okay. What is semaphore? Semaphore is a shared variable. Shared variable. Okay. And it can be initialized by any value, shared variable, and it can be initialized by any value, but it can be accessed by only two system calls. But it can be accessed by only two system calls, that is P and B. Some book calls P to be weight and some book call V to be signal. One and the same thing only. Okay. So semaphore is nothing but a shared variables only, and it can be initialized by any value. Whatever value you want, you can give them, but it can be accessed only by two system calls, that is P and B. So directly and directly what I want to say, if I say X is a semaphore, X is a semaphore, and in the code you write X plus plus, or you write X is equal to X minus 3 and all, you cannot do that. That means you cannot access them directly. If X is a semaphore, you cannot access them directly. Rather, there are only two system calls with the help of which you can access X, that is a semaphore, and these are P, V, or you can call them as wait and signal. Now, since we are using the word system calls are nothing but part of operating system. That's why I am calling them as OS based solutions. So now OS is helping in implementing CS. Okay, so I hope I have made the point clear. So now let me tell you the code of P and V. Okay, so let me jump to the next slide. Then I will tell you. Please take snapshot. Okay. Yes. So PS code is while S is less than equal to 0 semicolon S is equal to S minus 1. Okay. And Vs is S is equal to S plus 1. So we have written the code. PS is, see this, PS is while S is less than equal to 0 semicolon. That means infinite loop. We will go into infinite loop when S is less than or equal to 0. But if S is a positive number, say 1, 2, 3 and all, then we will decrement the S. Vs simply means you should increment the S by 1. That's it. Okay. So again and again, I am repeating, if S is a semaphore, then you can do only two system calls, PS or VS. That's it. So inside the code, you cannot do something yourself. Okay. That means you want to say plus 10, minus 20 and so on. Okay. We cannot do it. So if S is semaphore, then in PI process code, you cannot say S is equal to S minus 10. You cannot say S is equal to S plus 5 and so on. This is not allowed. That means semaphore cannot be accessed directly. That is the basic thing. Okay. So the basic thing is semaphores can't be accessed directly. Okay. That is, we have to use system calls. We have to use system calls to access them. Okay. And what are these two system calls? PS and VS. PS means this and VS means this. I think you have got the point. So now let me tell you a solution. Okay. So straight away, I will give you N processes CS based solutions. N processes CS based, N processes OS based solution. Okay. Or you can simply say N processes solution. Don't worry about it. We will say N processes solution by semaphore. You can say like this, N processes solution by semaphore. Okay. Yes. So what it will look like, see, we will say like this. For PI, I will say do while 1. So an infinite loop we will write. And what we are say, we will say PS, CS, VS. Okay. And S is a semaphore which is initialized by value 1. Are you getting it? So S is a semaphore which is initialized by value 1. And for PI, for n processes code we are writing. So for PI, we will write do while 1. Okay, do while 1. So this is infinite loop, and that we are writing PS, CS, and VS. Okay. Yes. So and because these are system calls PS and VS, so they are also atomic. You should remember these things. These are also atomic. Okay. So actually every system call is not atomic, but we are implementing them in such a way that they will be atomic. That means while executing them, we cannot imagine interrupt. So you cannot say while S is less than equal to 0. So one of the process has executed PS. Okay. And after this loop has been broken and we have imagine interrupt, and control goes to another process, and another process also has done PS. So it will execute this statement and interrupt come and so on. We cannot think like that. Okay. So we cannot imagine interrupt. So it will be both of these lines will be executed at the same time. And for VS also, this entire line will be executed. Only then we can imagine interrupt. So while execution of PS or VS, we cannot imagine any interrupt. So I hope I have made the point clear. Yes. So initially semaphore value is 1. So PI code I have written do PS, CS, VS, and while 1. Okay. So please let me know whether this code is correct or not. So first of all, we have to see the mutual exclusion part. Okay. Mutual exclusion. So I think see what we will do. So very first process. Okay. So for each and every process, the code is same only. So the very first process, whichever will come, it will say PS. PS means what? Control will come here. So it will say while S is less than equal to 0. So S is 1 now. So 1 is less than equal to 0, which is false. Loop is broken, and it will give S to be 0. Okay. S will become 0. So S will become 0, and since loop is broken, everything is okay. So it will enter the CS. So very first process will enter into the CS. Okay. And when it is in CS, other processes wants to enter CS, but they will do PS. So now please try to remember S is 0 now. Are you getting it? See, initially S is 1. Let me write it here. Initially S was 1, but the very first process which comes, it has made S to be 0. Okay. So now S is 0. So now what we will say, S is 0. So and it has entered the CS. What about other processes? When other process will come, it will say PS. Okay. So S is now what? See this, S is 0 now. So it will say 0 is less than equal to 0. Yes, it is true. So it will keep on rotating here itself. Okay. So it cannot do S is equal to S minus 1. So directly other process is waiting here only, PS only. Okay. So it cannot enter CS. And say for example, we can have say many processes, since we have n processes problem now. So let me write it. So take an example. So while taking an example, we can say P1 process is there. Let me write it here. Okay. P1 process, P2 process, P3, P4, P5. 5 processes are there. P1 executed this PS first, so it enters the CS. And P2, P3, P4, P5, they come and they are waiting here itself. Okay. So in PS only they are waiting. Why? Because all of them, P2, P3, P4, P5, they will see semaphore value to be 0, and we will say 0 is less than equal to 0, which is true. So uh, they will loop around here itself. Okay. Yes. So directly indirectly, I think you have got it. Mutual solution is satisfied. Okay. So two processes cannot enter at the same time. Why? Because only one of the process will see semaphore value to be 1. It is just like lock type. We have studied test and set type function. That is just like that only. If you try to remember, this is just like that only. While test and set lock CS lock is equal to false. Okay. Same scenario. Just try to imagine this thing. Okay, now, so mutual solution satisfied. What about my progress? So obviously, the processes who are waiting here in this loop, so directly indirectly, they wants to enter CS. That's why they are waiting. Okay, so only so obviously one of them, see this, they are waiting here. Now, when P1 was in CS, when it comes out of CS, it will do VS. VS means what? S is equal to S plus 1. Directly, you will do S is equal to S plus 1. So now S has become 1. Okay. Yes. So P2, P3, P4, P5 all were waiting outside the CS. Okay. And we can say since now S is 1, so exactly one of them will see S to be 1. Okay. And it will enter the CS. Are you getting it? So one of them will see S is equal to 1. So it will make it 0 and it will enter CS and so on. Okay. And in fact, we can say like this also. If P1 priority was more after doing VS, again it wants to enter, then also it can enter. Are you getting it? So when it comes out of CS, semaphore value was become 1, and then when it again wants to enter, it can see PS to be 1, S to be 1, and it can enter again. Okay, so I hope you have got the point. And so willingness point part for progress, willingness point is satisfied. Why? Because obviously process who are waiting here, so only one of them will enter into the CS now. Who are waiting here? Waiting here means what? They are willing to enter CS. That's why. Okay, and the time foundation. Yes, time foundation is also there. Why? Because obviously one of them will enter into the CS. Obviously one of them will see S to be 1 and it will enter the CS. When P1 will comes out of CS, it will make S to be 1. Then one of them will see it and it will enter. There is no question of deadlock and all. Okay, so last is bounded waiting. What about my bounded waiting? So I have told you just now that when P1 comes out of CS, it can enter again. And you can also say this P1, P2, P3, P4, they are keep on going, but P5 is never getting its turn. So algorithm is not deterministic. Algorithm should be deterministic, but here there is no determinism. Why? Why there is no determinism? Because we cannot guarantee who will enter the critical section next. That is the basic problem. So bounded waiting is not satisfied. So I hope I have made the point clear. Okay, so this solution is not good because bounded waiting is not satisfied. Okay, yes. So please take snapshot. I will jump to the next slide now. Okay. So other solutions also we can see. So for example, they can give like this also. So P1 process, P2 process, and so on. This is a gate question, P10 gate question. So 10 processes we have. P1 code is PS, CS, VS. P2 code is also PS, CS, VS. Okay, but P10 code is you have shifted it VS, CS, and PS. Are you getting it? So now they are saying S is initialized to 1, semaphore, S is semaphore initialized to 1. So how many processes, at most, how many processes can enter in CS? At most, how many processes can enter CS? That is the question. Okay, so it's just you can say attitude kind of question. Okay, so S is 1. So P1, P2 up to P9, one of them will enter into the CS. So let us suppose P1 enter the CS. Okay, and S was initialized to 1 and now it has become 0. P1 is in CS. Now since P1 is in CS and S has become 0, so P2 to P9 they won't enter. Why they won't enter? See the code. S is less than equal to 0, they will see it and they will keep on rotating here. But what about P10? P10 is VS. VS, there is no loop and all. It will simply do S is equal to S plus 1 and it will enter the CS. So obviously after P1, P10 can enter CS. And the moment P10 enter the CS, it will make VS. Making VS means what? S is now 1 again. So now from P2 to P9, any other process can also enter, say P3 enters and so on. So indirectly, what I will say, at most, how many processes can enter CS? 3 processes can enter CS at a time. At most 3 processes. Okay. I hope I have made the point clear. Why at most? Because it may be the case that no one wants to enter CS. Okay. So 0 may be the answer. So that's why they have used proper terminology. That means at most how many processes. So I hope I have made the point clear. Let me jump to the next slide and I will show you another question. Okay. So now they are saying, say P1, P2, P3 up to P10. We have 10 processes and all of them have same code. PS, CS, VS, dot. Every process is having same code. Okay. So now if semaphore value is initialized to N, then at most how many processes can enter CS? At most how many processes can enter CS? So this is a general question. So let me say, for example, S is equal to 3. When semaphore value is 3, we have initialized. See, I have told you, na, semaphore means what? We cannot access them, but it can be initialized by any value. So we are free to initialize semaphore with any value. So I am initializing semaphore by 3. Okay, but I cannot access it directly. Okay, that means I cannot do addition, subtraction, and all. For that, we have only 2 systems called PS and VS. That's it. Okay, so initialize to 3. So now I'm asking how many processes can enter into the CS. That is very easy question. See this. See the code. You will get more clarity. So let me write it. No doubt. Let me write it again. Okay. So what was the code of PS? PS was while S is less than equal to 0, S is equal to S minus 1. And VS code was S is equal to S plus 1. So what VS is doing, it is blindly incrementing S by 1. And what PS is doing, it is not blindly decrementing S by 1. It is first checking when S is 0 or negative, then it will not decrement it. Otherwise, it will decrement it. Okay, so now when S is 3, you will say here 3 is less than equal to 0. No, so you will make it 2. So let me write it. S is 3. So 3 is less than equal to 0. No, you will make it 2 and one of the process will enter into the CS. Let us suppose P1 enter the CS. Now P2 comes and P2 will check what? Semaphore value to be 2. So 2 is less than equal to 0. No, so it will make it as 1 and it will enter the CS. P3 comes, P3 will see 1 is less than equal to 0. No, so it will make it 0 and it will enter the CS. So directly in direct, and now no other process can enter CS because semaphore value is 0. So 0 is less than equal to 0. They will keep on rotating here itself. So now 3 processes can enter CS. So at most, how many processes can enter CS when S is 3? 3. So for when S is N, now you can generalize N processes can enter CS at a time. At most, N processes can enter CS at a time. Okay, so I hope I have made the point clear. So this is the basic thing. Please note down carefully. I will jump to the next slide. Okay, I'm jumping now. See this. So now they are show another gate question. So they are saying PS1, PS2, CS, VS1, VS2. For P2, code is PS2, PS1, CS, VS1, VS2. So now they are saying, is this solution deadlock free? So in place of using one semaphore, they have used 2 semaphores and initialized. S1 is initialized to 1, S2 is also initialized to 1. And now they are asking, is this solution deadlock free? That is the question, gate question. Yes, so is this solution deadlock free? So we will check. See, so directly indirectly, they want to ask about progress. Okay, because when deadlock comes, then progress fails. Na? Okay, so when deadlock is there, progress is not there. And more precisely, I should say progress, we have to check 2 things, willingness and time boundation. So when time boundation fails, then I will say deadlock will occur. That is the basic concept. So for progress, I have told you how we will check for line by line interrupt. So indirectly for deadlock free solution, I have to check line by line interrupt. Line by line interrupt. Okay, so if everything is fit and fine, you will say like this. See, S1 is 1, S2 is 1. So P1 comes, S1 it will become 0, S2 it will become 0, and it will enter the CS. When P1 is in CS, then P2 cannot enter CS. And when it comes out of CS, then P2 can enter and so on. So there is no deadlock. No, we cannot say like this. Okay, I have told you, we have to imagine line by line interrupt. So let me write it here. S1 is 1, S2 is 1. So first of all, P1, suppose P1 comes, it will do PS1. PS1 means what? S1 now will become 0. Now you will imagine interrupt. Control comes to P2. What P2 will do? PS2. It will make S2 to be 0. So now P1 will try to do PS2, but it cannot do because it was 0. So it will keep on rotating here itself. And what about my P2? P2 wants to do PS1. S1 is 0, so it will keep on rotating here itself. So directly and indirectly, no one will enter the CS. So it is deadlock free? No, it is not deadlock free solution. No. You may be thinking that it is deadlock free, but it is not deadlock free. I have told you, and how we will check it out by line interrupt. Okay. So I hope I have made the point clear to everybody. Okay. So this is all about semaphores. So that's it. Okay. And yeah. So we can do one more thing. Let me give you an application of semaphore so that you get more clarity. Let me jump to the next slide. Okay, so one of the application is, of course, it is used in implementing a critical section problem. Okay, so applications. Applications of semaphores. First application is, it is used to implement CS problem. It is used to implement solution to critical section problem or critical section problem solution. One and the same thing. Okay, it is used to implement CS problem solution. And second application is we can achieve partial concurrency. Partial concurrency. Okay, what do you mean by partial concurrency? Let me tell you that thing also. Okay. So what is partial concurrency? For example, see, we have PI process and here we have written its code. We have PJ process, here also we have written its code. Okay, and in PI we have a statement, say here we have a statement Z is equal to X plus Y. Okay, and here say we have a statement A is equal to Z plus B. So now you will say, sir, first we have to do this thing and only then we can do this thing. So that means first we have to execute PI, and then we can execute PJ. Okay, why we have to execute PI first? Because it will calculate the value of Z and then this Z will be used in PJ. Okay, so but see, there are of course I have drawn only 3 lines, but there can be multiple lines here and there in PJ there can be multiple lines here itself. So directly indirectly I want to say what you have done, you have executed entire PI and then you are executing entire PJ, but actually these lines before Z is equal to X plus Y and lines before is equal to Z plus B, they can be executed concurrently, but you are not doing that thing. So since you are not doing that thing, so it is not a great idea. So we can use here semaphores to do these kinds of things. Okay, so what we can do, so we will say, see, we will apply lock here. Okay, so directly indirectly what I want to say, when PI and PJ, these lines are executing, then there may be chances that it entirely depends on operating system. So PJ A is equal to Z plus B, Z plus B can be done first. It is not guaranteed that A is equal to Z plus B will be done after Z is equal to X plus Y. We cannot guarantee this thing. Okay, but we want to guarantee here. So what we can do, because see, if they are running parallelly, we cannot guarantee that. So the only solution was first you have to execute entire PI and then PJ. But it was not good idea because PI first few lines and PJ first few lines, they can be executed parallelly. But the moment we try to execute them parallelly, there is no guarantee that this line will be executed after this line. So directly and indirectly what we can do is, so we want that this line should not be executed first. This line should not be executed first. So I will apply here lock. I will say P of S. Are you getting it? I will say P of S. And here, see, after doing Z is equal to X plus Y, we can do this line. Nah? So here I will unlock. I will apply BS. So now by common sense, you can say S should be initialized to 0. Why? Because when S is initialized to 0, so it will do PS and it will keep on rotating here itself. It will not execute this A is equal to Z plus B. Okay. Yes. So directly indirectly, when control come to PI, it will execute this Z is equal to X plus Y. And after that, it will do VS. VS means unlocking. Unlocking means S will become 1. When S will become 1, then it can do PS and loop will be broken. Of PS loop will be broken and it will do A is equal to Z plus B. So I hope I have made the point clear. If you have any doubt, you can rewind the video and watch it again. So the basic thing is we have achieved partial concurrency. I'm not saying true concurrency. Why? Because these two lines cannot be executed parallelly. Okay, so partially we have done concurrency. That means few lines of PI and few lines of PJ can be executed concurrently. That's why I'm used the word partial concurrency can be achieved with the help of semaphores. Okay, yeah, so that's it. So here we have completed the semaphores also. So now in the next class, we will study classical problems of operating system. Okay, so now we have studied all the things. See this. We have to study 3 solutions. Software based solutions are over in the previous lecture. In this lecture, I have covered both hardware based solutions and OS based solutions. Okay, OS based solution was semaphore, hardware based solution was your test and set function and all. Okay, so that's it. So this is over. So in the next class, we will study classical problems of operating system. Classical problems of operating system. Okay, so I think you already know producer consumer problem. Okay, and we have other problems also. Don't worry, we will study them one by one. Okay, so we will study them. Okay, yeah, reader writer problem is there. Okay, and dining philosopher problem is there. So basically we will study three problems only. Okay, bounded buffer problem or producer consumer problem, then we will study reader writer problem, and then we will study dining philosopher problem. Okay, and after that we will jump to deadlock. So I think in 1 or 2 lectures, maximum 1 or 2 lectures, we will complete this process management part, and then we will study memory management part. In memory management, we will study only two topics, paging and segmentation. That's it. Okay. Thank you so much. Bye bye.